This video is based on a recent paper that shows how Hilbert spaces do not handle infinity in a way that is physically meaningful. Infinity in physics is potential. We can imagine to measure higher and higher value. We don't measure an actual infinity. Hilbert spaces treat infinity as actual. They include states, pure states, not statistical mixture, that have, say, infinite average energy or infinite average position. Which is kind of a problem. Where am I supposed to put the detector? But worst of all, the same state can have finite position for me and infinite position for you. And I think the principle of relativity may have a tiny problem with that. But wait, there is more. You can evolve a finite expectation to infinite expectation in finite time. And then evolve it back to finite expectation. So you oscillate from finite to infinite, and so on. And if you are like me and want to make sure that our physical theory are really about things we can produce and measure in a lab, it's a problem. And you may also know that quantum field theory have problems with infinity. Maybe, just maybe, these are related. And if we understand to fix the first, maybe, just maybe, we at least fix some of the others. You see, to me, all of this seemed quite an obvious problem, and I didn't quite understand why this hadn't already been highlighted and addressed. Then we went through peer review.
The question of whether the limited states are actually physical or merely idealization is rather pointless.
Is it really such an outrageous proposition that the math should represent physical things in a physical theory? And if you want, I'll make a separate video to go through that and how I'm now very skeptical that we'll ever converge to a solid foundations of quantum mechanics. But while ranting is fun, it doesn't solve the problem. What does solve the problem? What we always do here, go through the details. And this is what we're going to do. First, we're going to see what it means to have a physical mathematical definition, how ideally the mapping between math and physics should work. Then we break down the mathematical definition of a Hilbert space and see what properties correspond to physical requirements and which do not. A Hilbert space is a vector space with an inner product. This part we need. It is physical because without it we can talk about entropy, statistical mixture, probability, and so on. We would not have the physics. But a Hilbert space is also closed under Cauchy sequences. This is what brings in the bad infinity. And we'll see how. This is the part that we would have to strip out. That's the problem. And we'll see how Schwartz spaces in some cases are much better, but they're not a general solution. And so the point of this video is let's at least realize we have a problem. So let's get started. Let's first talk about the relationship between math and physics so it's clear what it means when I say that something is physical or unphysical. So, on the left side here we have the physical world with all the things we have in the physical world, the physical states and the physical system that we want to describe. Then on the right side we have the mathematical representation, so the Hilbert spaces for quantum mechanics, the phase space for classical mechanics, the field configuration in field theories, and we are going to have some map from the physical objects to the mathematical representation. Now, deciding which is the correct mathematical representation for the problem at hand, which idealization work and which do not. This is the whole physics problem, right? And we're not going to have a one-to-one map because we're going to use the same mathematical model for different physical objects. But, you know, when we have all those issues resolved, the idea is that we should be able to take an object in the physical world and have a clear idea how we are represented mathematically in the mathematical world. Okay, so these are all our well-defined objects, and on the left side instead we have all our different physical objects prepared in a different way. We have a way to map physical objects to mathematical representation, and then in the math we do operations. We evolve the things, we make calculations and so on. And so we're going to have some maps from mathematical objects to other mathematical objects, and what we'd like to have is that these mathematical objects actually map back to objects in the physical world, right? So that they are not just mathematical objects, but we can go back, right? And of course, going back again, since we had a map that was not unique in before, we have to sort of disambiguate, but it's clear that if we started with this object instead of this object, then the future evolution is going to be that object at a different place, right? We're going to be able to make this to close the loop with the extra bit of physical information that is not represented mathematically, right? So that's what we like to have. What we don't want to have is somehow the mathematical representation that does a calculation and maps to something that it's ill-defined in the physical world, that there is no physical correspondence for the math that we used, that we had. Another thing that we don't want is to have a well-defined mathematical object that map to an object that is not well-defined mathematically, because then what is it that we're doing in the math? We're just doing nonsense, so we don't really have good math, and that's something that mathematicians are good at spotting, that we don't want to do that. And then, of course, we also want to have, would not have the case where we have physical objects, possible physical configuration, but they don't have a mathematical mapping, right? So how we're going to represent that? We need to be able to represent everything that we have in our physical world, at least in some context. So the idea then is that a physical theory is well posed if every physical and mathematical object have a counterpart. We can go back and forth. So ideally, this is what we like to see. We have a physical specification that says, okay, we are looking at these types of objects in these conditions and so on. This maps to some mathematical definition that tells us this is how you're going to represent it exactly, and so on. And we have then all our mathematical objects given by the mathematical definition, and we're going to be able to go back and forth. So we say that a mathematical definition is physical if it captures and only captures an aspect of the physical system, something that is really physical about the system, and so that we can make mismaps. So we should really think of mathematical definition as really physical specification, right? So we have two objects, we can put them together to make a composite object. Well, we're going to have some type of mathematical operation that represent this, and that mathematical representation has to conform to the specification of the physical operation of putting things together. So, for example, it has to be symmetric, because if we put A and B together, it doesn't matter that we're putting A together with B or B together with A. So that's basically the idea. And to give you some sort of a more concrete example of what it means to have something that it's an unphysical mathematical definition, suppose we're looking at the inertial mass in Newtonian mechanics. So we have a force applied to a mass, and we have an acceleration, right? And these are going to be represented by some mathematical objects, and we could say, well, the mass is going to be represented by a real quantity, so it's a real value. And this presents a problem, because a mass in physics cannot be negative, right? If we had a negative mass, it means that if we push it in one direction, the acceleration actually goes against where you're pushing, which would not make much sense. Or that mass is also have to be the same for an apparent force, and now you have everything that is stationary, and some have positive mass and some have negative mass, and all these objects are stationary, and now suddenly you introduce an apparent force because you start running in that direction, and some of these things you see them going backwards, and some of them instead you see them coming together in your direction, which wouldn't make sense. So they all are standing still, actually, right? So a negative mass does not make sense, and it's the physics that tells us that the mass cannot be negative. It's not the math. It's a physics specification that tells us, look, the problem at hand, what we're doing, doesn't make sense that we would represent an object with negative mass. It's not going to work like that. And so, even with this simple thing, you can start, I think it's a good exercise to think about what are the limit case of physical system, which is something that in physics we don't quite do that well. And so you can think, well, can the inertial mass be zero in Newtonian mechanics, or does it have to be positive, right? Would it make sense in Newtonian mechanics to have a zero mass? Or we have a slight distinction, right, between inertial and gravitational mass. In principle, there are two different objects. One tells you what happens when you apply forces, and the other one is the charge for the gravitational interaction. And the principle of equivalence tells you that they have to be the same, but does the gravitational mass has exactly the same constraint as the inertial mass of Newtonian mechanics, or they are different things, right? You know, should think about it. It's good to think about these things, but we're not going to think about those things in this video. We are going to talk about Hilbert spaces and whether they're suitable for representing the states in quantum mechanics. So mathematically, what is a Hilbert space? Well, a Hilbert space is a vector space, meaning that we can do addition. We can take two vectors and make a linear combination of them with some complex coefficient, because we're going to be using a complex Hilbert space, because that's what we use in quantum mechanics. Then we have an inner product, meaning that if we get two elements, we can define an inner product that gives us a number, and with that we can also define a norm and a bunch of other things. It is Cauchy complete, meaning that if we have a linear combination of vectors such that the coefficient, the square of the coefficient converges, then what happens is that this vector actually exists in the space. So the sequence, this infinite sum converges in the space. Actually, as we'll see, the definition of Cauchy completeness is a little bit more complicated, and we'll see that later. This is a nicer equivalent definition that actually it makes a little bit more physical sense, at least to try to interpret. Right? So basically, the Cauchy completeness tells us which infinite linear combination are allowed. And since it's something about infinite linear combination, if you are in a infinite dimension, you automatically have that property, and it's in infinite dimension that the property is useful. It's something that it's useful in mathematics to be able to prove convergence theorem and so on, and that's where we actually have to see whether this property holds. So, of course, if you're in finite dimension, you're going to have a Hilbert space. The question is, do we always have a Hilbert space or not? Okay, so first, as I said in the introduction, we look at the vector spaces and inner product and to see whether we have a physical argument to require those operations among states, or we don't even have a physical requirement for that. So one of the things that we know in quantum mechanics is that we can make superpositions. We take two states and we make a linear combination, which we call superposition, and we can interpret this superposition as essentially some kind of making not a statistical mixture, but making another state where if we were to measure the first element, we would find it with the probability being C1 square, and the second elements with probability of C2 square, right? So there is a connection between sort of measurement and superpositions, linear combinations in quantum mechanics, and what we go and find in the physical world. Now, what is important to note, and this is something that I realized only because I did the due diligence to understand what these things are, is that actually having a linear combination is not enough to technically to know whether you have a superposition or what type of superposition you have. Because this interpretation, the fact that the square of this coefficient is the probability, is only valid if psi and phi are orthogonal states, if they are elements of the same measurement, possible outputs of the same measurement. So you need to be able to know what is the relationship between these two elements in terms of orthogonality. Otherwise, you are not going to be able to make any determination. And the reason is that if they are not orthogonal, then you would need the inner product to renormalize, and it's with the normalization that you're going to be able to recover the fact that there is some probabilities of what the probabilities are. So the linear space by itself is not physical, but the linear space with the inner product are physical, and we need to get these things to recover this interpretation of probability during measurement, of superpositions, and so on. Okay, so in principle, if we were fast and loose, we were saying, yeah, we need these things. But again, as I said before, like, what exactly is a superposition? Like, it's physically, what is it? Is it a purely mathematical decomposition, or is it actually a physical property? And also recall that states in quantum mechanics are defined up to a total phase. The phase is not really important. So of these two coefficients, C1 and C2, the phase is not important, it's a relative phase. So not everything about this linear combination is physical, some parts are not. And so it becomes hard to say, oh yeah, we need this. Do we need this actually? Like, is it like, what exactly what? And then we have the idea that inner product is about measurement, and measurement in quantum mechanics are a mess. They're subject to interpretation. People don't agree. And we want to have mathematical specification that is independent of what people say about their interpretation. We want our physics to not care about the interpretation. So we want to be able, and this is where I am, I want to be rigorous in this conceptual game. I want to have an argument that says, regardless of what interpretations you have, you need this inner product and vector spaces, right? That's what I want, so that I can go bed at night and be reassured that without caring the world, without caring about the interpretation, we need these axioms for the states in quantum mechanics. These postulates are there and they need to stay. Okay, so how do we do that? We have to transform this characterization of superposition and inner products in terms of something else, so that we are able to argue, oh yes, we are always going to need these things. And so what we have in the paper, which to me is the part that are interesting, because they go into this greedy little details, is that we have a theorem that tells us that a pure state psi is expressible as a superposition on other pure state phi I, right? So we can write psi as a linear combination of these elements here. If and only if there exists a mixed state rho that can be, and a mixed state is just a statistical mixture, right? It's not a superposition, it's statistical mixture. I prepare this state 30% of the time, this 20% of the time, and this other 50% of the time. I don't know which one I prepare, I made a statistical mixture. So, the psi is a superposition of the phi, if and only if there is a rho, a mixed state, that can be equivalently expressed, so they can be expressed in two different ways. One, as a mixture of phi's, right? So the elements that we're taking the superposition of, and psi plus some other thing, right? So the idea that we can express something as a superposition of other thing is equivalent to the fact that we have multiple decompositions of mixtures in terms of pure states. And this is something that only happens in quantum mechanics. It does not happen in classical mechanics. In classical mechanics, mixtures have a single decomposition in terms of final elements, pure states, point in phase space. There is only one probability measure that it's in terms of those objects. In quantum mechanics, instead, it's not like that. That's sort of the defining characteristic of quantum mechanics. And so here we're saying we're seeing that the superposition is really that property, the property that we have multiple decomposition. Okay, now the fact that we have multiple decomposition for mixed states in quantum mechanics, it's a fact of life. It's something that you can detect, or the fact that you can't detect, you can't tell whether, for example, you prepared a mixed state of 50% spin up and 50% spin down, or you prepared a mixed state of 50% spin left and 50% spin right. So you can't distinguish between these two mixtures. They are the same thing. That's why you have multiple decomposition. And since multiple decomposition is something that we see experimentally, right? Or we can't tell, we're not going to be able to distinguish experimentally, then that's something that it's in the physics. It's something that we have to have. So superposition is equivalent to multiple decomposition, and since quantum mechanics allows multiple decomposition of mixed state, and this is something that we measure, therefore it must exactly allow the linear combination of those vector space, right? So the physics, the thing that I want to say I need, is the multiple decomposition. That's interpretation independent. Every interpretation will have to tell me that quantum mechanics allows for multiple decomposition because it's a physical thing that we can measure. Therefore, we're going to need superposition. Good. What about the inner product? How do we characterize the inner product? Well, we can characterize the inner product through the entropy. Again, an attribute of mixtures. And again, the mixture, the entropy is something that we measure, that we characterize. We have the whole theory of field of quantum information that is based on the quantum entropy and the fact that you can go and measure and you can do things. And so we have another little theory, another proposition that tells us that the probability of measuring phi having preference psi can be uniquely determined by the entropy of their equal mixture. So we can have here the probability of measuring one with respect to the other. That's the Bohr rule, right? And that's the thing, oh, it's measurement, I don't know what it is, whatever. Well, okay, fine. But on the other side, we have an unequal mixture. And we can define an entropy for that equal mixture. That entropy depends on the square root of the probability and depends it in a way that it's invertible, right? It's bijective. You can go from one to the other and back. So knowing the inner product is exactly knowing the entropy. In fact, it's not exactly the inner product. You see, there is a square. So it's exactly the inner product without knowing the phase. So the total phases, you're not going to be able to recover them from here, and you recover everything else, all the things that are measurable about the inner product, you recover from here. So here you're recovering exactly the part of the inner product that is physical, that you can actually go and measure, and it corresponds to the inner product. So if we need to be able to have an entropy well defined, which we need experimentally, then we are going to have the inner product with exactly the same values that we would have in quantum mechanics. So quantum mechanics allows multiple decomposition of mixed states. Quantum mechanics allows the entropy. Therefore, we must have both. So complex inner product spaces are physical when used to represent the state space of quantum mechanics. They represent and only represent mathematical property with a clear physical correspondence. Linear combination represents statistical mixing and superposition, because we saw that whenever we can do statistical mixture in quantum mechanics because of multiple decomposition, we are going to have superposition, and the inner product represents the entropy and the probability of measurement. Okay, so as we saw before, Hilbert spaces also have Cauchy completeness. So where does this come from? What it is exactly, and so on. As I said before, Cauchy completeness, the definition that we're going to go through here is a little bit complicated, but I think you should at least see it once. You can always skip it and go at the easier characterization, but we should actually go through it. And what I should stress that Cauchy completeness has nothing to do with the fact that you have a complete basis for the Hilbert space. You always have that. And I say that because one of the reviewers apparently didn't understand the difference. So, yeah. So what is Cauchy completeness? Okay, so if we have an inner product space, we can define a distance. How do we define a distance? We take the two vectors and we take the difference between them and we look at the norm of the difference. The closer the vector are together in the space, the more the difference is going to be closer to zero, and it's going to be zero if and only if the two elements are the same. It will also satisfy the triangle inequality, so this is actually a distance function. So we have a distance, and now we want to define a sequence of states, right? A countable sequence of states where the distance between the elements become small. And what does it mean? How do we define that the sequence of the elements, the difference between the elements become small? So imagine that we have the sequence, right? This is the sequence. And we also get the sequence here. So we have the sequence twice. And for every pair, right, of elements in the sequence, we can calculate the distance. So the first element here is the distance between the first element to the first element, which of course is going to be 0. And then you're going to have the distance between the second elements of the first, this is distance for the third elements of the fourth, and also the distance between the first element of the third, and so on. So you have all those different pairs, and you have calculated all the distances. So what does it mean that the distances become small? How do we want to characterize? So we want to basically say whenever we pick an R, and an R is basically going to be a cutoff between the distance. So whenever we pick an R, we can find an N, right? We can go farther along the enough inside the sequence such that after that all the distances for all the elements that are after n, they are smaller than that cutoff. So, pictorially, if you imagine that this is the full set of differences, if we pick an n, you're going to look at these, all the elements that are inside this sort of infinite rectangle that starts there, and all the elements there are going to be less than r. This is what a Cauchy sequence is. This function cares about the norm of the elements, and we don't care about the norm of the elements because we basically think that everything is normalized. So this description of Cauchy completeness and Cauchy sequences is a little bit difficult to understand physically for the purpose of quantum mechanics. So fortunately, there is a different characterization. Suppose you have an orthonormal basis, so countable elements where everything in the Hilbert space is just a superposition of those. Then we can always form a linear combination where all the coefficient, the sum of all the square of all the coefficient is finite. So if we have a sequence of coefficient that their sum square, the sum of the norm is finite, we can always use it and make a linear combination. Now, the thing that we're going to care, of course, is when the sum of the squares sums to 1, because that's what we were doing in a superposition where we're making a probability. And we're guaranteed then, if the coefficients sum to 1, that the superposition exists. So basically what this tells us is that we can always make a superposition of countably many elements in the Hilbert space. This is always gonna work. Right? So this is mathematically nice because it's kind of like very, very symmetric, if you want. Like we can complete the space. It's always nice. We can always have all these sequences. But again, the problem is it's physically nice. Does this make sense in the physical world? Okay, suppose we have an operator n that counts the number of particles, and therefore these i's are the eigenstates with I particle. The expectation of n is given by this expression, and since psi can be seen as, any psi now, can be seen as a linear combination of the bases, we can decompose our psi with our components. Now, since I is an eigenstate of n, then n comes out and we just have the eigenvalue here. So the total expectation is just the I weighted by the probabilities that we get from the coefficient. So it's essentially I times the probability of having I. That makes sense. Okay, but here's the thing. We are guaranteed that the sum of the Ci square sums to 1, but if we multiply this by I, we are not guaranteed that this actually converges. We could have a state, a superposition of different particle states where the actual probability converges, but the expectation of the number of particles diverges. We would have infinitely many particles in a pure state. So, how do we do that? Can we get a counterexample? Yes. So we can set that Ci is equal square root of 6 over pi I. And again, this I is not the imaginary unit. This is the index, right? It's 1, 2, 3, 4, 5, and so on. And so if we do the norm, that would be the sum of the ci square. So it's 6 over pi square, 1 over I square. And this series actually converges to 1. So we have a normalized state, everything works, we are in the Hilbert space, things are good. But if we now do the expectation, we're going to take this and multiply it by an I. And now we have the harmonic series. We have the sum of 1 over I, and that diverges, it goes to infinity. So the expectation would be infinite, right? So yes, we have all the states and all the probability sum nicely, but then we get these infinities, and this is the problem. These are things that might not make physical sense, because what it doesn't mean that we prepare a state with infinitely many particles. Does it make sense or not? So here is the rub. Every continuous linear operator defined on the whole Hilbert space is bounded, meaning that if we want to have an Hermitian operator such that we always have an expectation value well defined for that operator for all states described by Hilbert space, then the space, the operator has to be bounded. It has to have a maximum and it has to have a minimum. So every continuous unbounded operator then is not going to be defined on the whole Hilbert space. There is going to be some states where it's infinite, so it's not well defined, or some states where it's really doesn't even converge, right? It really does not make even sense of talking about it. So things like position, momentum, energy, number of particles, all these things are unbounded operators, and we need these things, and there are going to be states for which these are not well defined. Again, this is, if you talk to a mathematician, they will say, yes, of course, it's like that. So there is no surprise. And the problem is, of course, is in the physics, because if we say that we need infinite dimensional spaces to model quantities that are unbounded, the fact that they have no upper or maybe lower limit, right? We could always measure something bigger, right? In principle, because that's the model that we are going to go for. Then Hilbert spaces forces us to include objects for which the expectation of those quantities is actually infinite, right? So the infinity is not potential anymore. It's not just, we can always measure something bigger, like we have, for example, in classical mechanics without any problem. In a Hilbert space, instead, there are going to be states for which the expectation, again, pure states for which the expectation is actually infinite, or it's not well defined. And this is a problem. So what we have here then, that the vector space structure and the inner product structure, these are well defined, we saw, physically justified. But the Cauchy completeness, it's something that does not make sense. We cannot guarantee it. If you think about it, we saw that superposition are actually equivalent to statistical mixture. Well, we can make finite statistical mixtures no problem. Infinite statistical mixture, that's not something that we can do. And if you think of a statistical mixture that has some infinite value, well, that statistical mixture is not all the values, we get something that is increasing every time. So it's kind of like we don't have really a preparation that it's always equals to itself in time, because the thing has to be leveraged. So infinite statistical mixture is especially if they lead to infinite expectation, it's something that we cannot physically justify. They're not physically motivated. This part is unphysical in that sense. It's not going to represent, it's not justified by the physics. It will not represent things that exist in physics. Okay, and this is how most physicists work. Yeah, okay, whatever. Can't we just ignore the bad states, right? Everybody else does it. You just ignore the bad states, and you only get the good states, right? And the problem is this: if we were able to characterize which states were bad, right, we could also characterize the good state and then have a nice mathematical definition that tells you, yeah, these are the only good states and this is what we should care about, right? So, in a sense, I'm trying to do that and do it properly. So we should go and look. We should be able to answer the question, which states are good and which states are bad. You could also say, well, let's just use them all, who cares? And the problem there is that in math, bigger is not always better. Like extending the space actually might create problems that you wouldn't have in the smaller space. So cutting the space right in math is useful, and a lot of the time if you cut it right physically, somehow you also get it correctly mathematically. So as an example, one of the things that we have in math and we also use a lot in physics are measure. So for example, you have a volume, like you have a space and you want to define the volume. So you want to give it a set and you want to know a number of that region that represents the volume. And one way to characterize volumes is through a measure on the Borel algebra of the Euclidean space. So a measure is a function that tells a set from a sigma algebra, and typically we are going to use the Borel algebra in this case, and it gives you a number from 0 to infinity. And what is a Borel set? Well, you can kind of think it as generated by union, intersection, and complement of parallelepiped. You get parallelepiped, you fill the space with all your parallelepiped, and you create a set. That set is going to be a Borel set. It can be open and closed. There are some details there, but essentially that's kind of how these sets are generated. But then you can say, okay, well, why do I have to restrict myself to this Borel algebra? Let's do it on all the possible subset, and not just the one constructing this way. Let's just do it on all the possible subset of the Euclidean space. Well, if you try to do that, right, then you would extend not just the measure from the Borel sets to the power set, like all the possible subsets. Then you bump into problems like the Banach-Tarski paradox, which is that thing where you can take a ball, divide it in 5 parts, and then move those 5 parts in different places, and then you end up with 2 balls that are of the same size. So you basically double the size. And this is because whenever you have infinities, you can do very clever and nasty things. And so saying, oh, let's just ignore the sets that are problematic, you can't define the measure on all the sets. So it's not that you have to ignore it. You have to find the right set. And actually, in our research, we show that the Borel set are exactly those sets that can be associated with experimental tests. So it kind of makes sense that in physics we do that, right? So can we simply ignore the bad states as everybody else does? No. Because we might be expanding the space too much, and then we would lose a nice property that states have, and maybe we're making our life harder to understand what the quantum mechanics is, just because we don't have the right mathematical structure. So no, we can't do that. And another reason that we can't do it is because if you try to ignore these things, you are going to get very nasty things from the physical side. And this is where I can give you some examples of things that I found that are not just counterintuitive, they just make no sense. So, okay, so what are the problems that this Cauchy completeness dragged in? So, let's say that we have these 2 wave functions here, right? The first one is just a Gaussian state. And it's just the square root of a Gaussian, so this is the probability density, and you recognize this is a Gaussian. And then you have the wave function corresponding to it, which is the square root of the probability density, and therefore that's just going to be a nice wave function. If you make the expectation of position, that's going to be the expectation of this probability density, it's going to be 0. That makes sense, the Gaussian is symmetric. And this particular Gaussian, the expectation of the position squared, the variance, is going to be 1/2. And I chose this because it makes some of the calculation later a little bit nicer. Okay, so this in blue is the Gaussian, but you see that there is this other reddish function. And this is not, it's still a bell shape, but it's not a Gaussian. You see that the tails are fatter, like they're fat, they are thicker, they are higher, there is higher probability in the tail. And again, the form of this function is still nice. It's 1/pi x squared plus 1. And so again, the wave function is just going to be the square root of that. And the expectation is still 0 because it's a bell shape centered at 0, so good. But the expectation of the position square is actually infinity. And you can imagine if we were to take this and multiply by x squared and integrate, right? You're basically integrating x squared of x squared. So you're kind of integrating a constant, and the whole integral is going to blow up. It's not going to be good. Okay, so now we have these two functions, both very good wave functions. They are in the Hilbert space, not an issue. The first one is a Gaussian, and it has a well-defined position and position squared. And the second one is not a Gaussian. It has a well-defined position, but the position square is infinite. It's like infinitely blows up. Okay, and then you can say, okay, what's the problem with this? Well, the problem is that you can get this infinite expectation from a change of coordinates. So we can have that the distribution is a Gaussian, the probability distribution as a Gaussian in one frame, and is that other distribution in another frame, right? So x is the position as measured by one frame, and y is the position as measured in the other frame, right? And so if we're able to do that, then of course the first guy will see that the expectation is finite, it's 1/2, and the other guy will see that the expectation for the other, like the variances, are infinite, right? And of course you can make this trick also with the actual position, right? If we cut it half and we only have half of the wave function and we set the zero the other side, you would have a finite position for one and infinite position for the other. We are going to use this because, again, it's nicer to make the calculation. You can actually see that we can actually get the functions and everything kind of works, and it's fun to see that the math works, right? So how can we find this coordinate transformation that takes one wave function and one distribution and brings it to the other, right? So the way that probability densities, any density work under a change of coordinates is the following. You have that the density on y times dy has to be equal to the density of x times dx, right? That's going to be the infinitesimal amount of probability that you have at x and y, and you always want those to be the same. And so we want to be able to construct a transformation that has this property and maps one thing to the other. Okay, so rho y, here we have it. It's 1 pi over y squared plus 1. And on the other side, we have just our Gaussian e minus 2dx squared over the square root of pi, right? Okay, now you can see that this is actually the derivative of the arctangent. And so this term here is just the differential of the arctangent y over pi. And on the other side, this is a Gaussian, and the integral of a Gaussian is the error function. So the differential of the error function over 2 gives us the original Gaussian. And that over 2 is there because of the variance. We saw that the variance was 1/2. Okay, so we want these two differentials to be the same, but of course these two differentials are going to be the same, especially if the two functions are the same. So if we set that the arctangent of y is equal pi over 2 the error function of x, we have an equality. And this is just two functions. Like, there is nothing wrong with picking this function. It's just two functions. And since this is the arctangent, we can invert it. So we have that y is equal the tangent of pi halves the error function. And you may recall that the error function is bounded from minus 1 to 1. So for x that goes to infinity, the error function is 1. For x that goes to minus infinity, it gives you minus 1. And if we multiply by pi halves, now this argument goes from minus pi halves to pi halves, which is exactly the range of applicability of the tangent. And this means that this overall thing is an inversible function. Now it's going to grow very, very fast, very, very quickly, but it's still bijective. We can go back and forth without a problem. It's just a coordinate transformation. It's a very weird coordinate transformation. It's probably something that in physics we don't want to use, but in principle we can do it. So if we say, oh, we want to be relativistic, are we ruling out that transformation or not, right? So if we say, okay, we should allow any coordinate transformation, then this should be allowed, right? Why not? Okay. But that was the transformation for the probability density. And you said, well, we actually need to transform wave functions. So how do you transform wave functions under coordinates transformation? Like, have you ever thought about it? Have you ever noticed that whenever you take a quantum class or look at a quantum book, coordinate transformations are never discussed? I don't know. I had to figure out these things by myself. But so how do they work? Well, okay, so if we have the probability distribution in x, we multiply by the derivative of x over y, and then we get the probability of distribution in y, right? And since the wave function square, the norm of the wave function is the probability distribution, what we need to do is just multiply the wave function by the square root of the derivative. And again, this is well defined because the function is bijective and so on. If we were in in multiple dimension, we probably need a Jacobian, so we need a positive Jacobian because it needs to be invertible, blah, blah. So there are all those things, right? But it's funny to me that when you study classical relativity or also classical mechanics, you think about all these coordinate transformation, you want to know how the object changes and so on. And then when we talk about the wave functions, nobody talks about it. And part of the people that reviewed the article, they clearly had very, very confused idea of how this all works. But okay, so we have our wave functions, we have our coordinate transformation, we have the wave function in x, and we have the wave function in y. So now we just want to verify that actually this works, right? This actually works. And the way that we're doing, instead of converting x into y, it's actually easier mathematically just for the calculation to go from y into x. So let's calculate the derivative of y with respect to x. The derivative of the tangent is the secant square. So we get the secant square of pi half of the error function of x. And then we need the derivative of the error function, which is the Gaussian minus some coefficient because we have that 1/2 and pi. So we get this term here. Now, you might not know, but you can go check that the secant square is actually equal to the tangent square plus 1. That's actually how you create, you go and find the integral of 1 over x squared plus 1. You find the arctangent because there is this relationship. So, okay, so we have the tangent square plus 1 times that essentially the Gaussian is equal to the derivative of y over x. But note that y is equal the tangent, right? And so this tangent square is just none other than y squared. So the derivative is y squared plus 1 times square root of pi e to the minus x squared. Now imagine that you take the square root of this and then you multiply it by this term here. What's going to happen is that the y squared plus 1 is going to simplify, and you are going to get the Gaussian terms with the pi fixed. So really, we are going to be able to do the coordinate transformation, and everything is going to work fine. Now, another thing that people somehow don't have clear is that coordinate transformations in quantum mechanics, since they are changes of representation, they are unitary transformation. In fact, if you imagine here that we can put here any wave function, right? We're just taking the wave function and multiplying with something else, right? This is going to be a linear transformation, and it's going to preserve the integral because we saw that the probability distributions are going to be conserved. So this the wave function is going to preserve the norm. So we have unitary transformation that preserve, we have linear transformation that preserve the norm. Those are going to be unitary transformations. So coordinate transformations are unitary transformation. But here's the kick. Also time evolution are unitary transformation. So can we use this trick to make a unitary transformation in time that evolves things, that evolves one function into the other? And again, the way that you should think about unitary transformations in quantum mechanics on the Hilbert space, they're rotations, right? You're taking a vectors and making a rotation. All unitary transformations are just rotation. So if you have two vectors, you can always rotate one vector into the other vectors. Right? There are two unitary vectors. You can always find a plane where you can take this and rotate it one into the other. And then you will keep rotate, and you're going to bounce to those two states over and over and over. That's what unitary transformations are. And so we're going to be able to do it. Of course we're going to be able to do it. How do we do it? Okay, so suppose that our rho of x and t is the evolution of the probability in time. So we have a wave function in time, then we make the square and we take this probability distribution. Okay, so we can make it that at the even times, right, at the integer two ends, right, we have the Gaussian, and then at the odd intervals we have the other function, the one that blows up. How do we do it? Well, imagine that you're doing some type of evolution of every point. So we're taking all points in x and we're moving them in time, right? We're moving them in time. They're going to be a different position. So we say that and we're going to move them back and forth with some cosine and sine that tells us the frequency of the exchange. So at even times, when this cosine is going to be 1 and the sine here is going to be 0, we want to have x. We want to have the original coordinate. At the odd times, instead, we want to have the transformation. We want to be able to jump into the tangent of the error function. And if we do that, again, we are going to have some rho and therefore also a psi that depends on time. And we're going to find that the expectation of the variance is going to be 0 at even time and is going to be infinite in infinite time. And the cool thing is that this thing actually corresponds to a one-parameter family of unitary operation ut that is strongly continuous, meaning that if you take different t's that converge to a t0, well, the operator is also going to converge. Therefore, from what I understand from mathematicians, you're going to be able to find a Hamiltonian, and okay, the Hamiltonian is probably horribly complicated. We're not going to be able to write it down. Maybe, I don't know. Maybe we can, because we have been able to write a lot of things. But still, conceptually, that Hamiltonian is going to exist. Therefore, we're going to have a possible time evolution that does these things. And this is one example of there are going to be infinitely many crazy unitary evolution that are going to be doing things like this. And again, how can we say that they're physical? How can we say that something that takes a distribution, blows it up to infinity, and then brings it back infinite time, back and forth, back and forth, back and forth? How can we say that that's physically useful, meaningful? And how can we work with state spaces that have these properties? Like, we should not. We should have math that makes sense physically, and it's also mathematically precise, mathematically consistent. So at least that's how I see it. Okay? So there are other hints that the Hilbert spaces are really not that good for physics, and I'll give you a couple of our ideas. So all Hilbert spaces that have bases with the same cardinality are isomorphic. So if we have a two-dimensional Hilbert space, that's going to be equivalent to a two-dimensional Hilbert space, a two-dimensional, three-dimensional Hilbert space. They're not going to be equivalent to each other. The math is going to be able to tell you, oh, no, yeah, you can't go with a unitary transformation from one to the other. These two things are different. But all the spaces that have countable bases, they technically have the same number of bases, and so they're equivalent. And so if we take the space of wave function on Rn or Rm, right, so different numbers of degrees of freedom, they all have countable bases, and you can basically look at that because you can take the eigenstates of the harmonic oscillator in all the orthogonal directions. You can diagonalize, you're still going to have a countable basis. This is, again, how infinity works. If you take the product of finitely many countable infinity, you basically get another countable infinity. You don't go up in dimensionality. So these two things are the same thing. The state space for 1 degree of freedom is exactly the same state space in quantum mechanics of 1 billion degree of freedom. And note that this is not true in classical mechanics, because Rn and Rm are not are not even topologically equivalent. Like you can see that you have a three-dimensional space or a billion-dimensional space. So if you have two phase spaces, you can't go from one to the other with not even a continuous transformation, right? It's not that I can do it continuously, but then I can do a diffeomorphism. No, you can't even do it continuously. Here you can do it through a unitary transformation. For the Hilbert space, you can do it. So that kind of does not quite make sense, right? That the two spaces over which we define the wave functions are different, but the space of wave functions we construct over those spaces are the same. That doesn't make much sense. And if you take this literally, then what would happen is that it means that there exists a unitary transformation between the state space of a single particle and the state space of a billion particles, right? Imagine how good would that? We could make a hard drive that is just one single particle, and we can keep cramming over and over as much data that we want. And again, it does not make sense. It does not make sense. Okay, so going back to the original diagram, I think we are in this case. We are in a case where we have our physical world, we have mathematical representation. With the mathematical representation, we can map to other objects that are well defined mathematically, right? At least. Not according to intuitionists. Intuitionists are going to tell you that this is all junk anyway. But according to a lot of mathematicians, mainstream mathematicians, they will tell you, yeah, that objects are mathematically well defined. But then when you try to go and reinterpret those objects with the physics, that they do not correspond to cases that are physically meaningful. So if we work with Hilbert spaces, the problem is that our theorem might also work on these non-physical objects. So I worry that we're making the job a lot more complicated than it has to be, and that we're missing out. We're missing out maybe on nice theorem, nice constructions that would allow us to give better intuition on quantum mechanics itself. Maybe not, but I would think that, getting the math right is probably long-term. It's going to be a good thing. And again, we have been using this math for like 80 years. The guy, von Neumann, who was the proponent of Hilbert spaces, from what I understand, just a couple of years after he published the book, he regretted the decision of Hilbert spaces. He didn't like them anymore, and then is dedicating the rest of trying to find better constructions, better mathematical objects, and he wasn't satisfied by any of them. But the point is that it's not that the guy that presented this and nobody found any problem. No, people somehow know that there are these sore issues, and we never hear about them, and we never try to solve them. And instead, we talk about interpretations and hidden variables and so on. I want to fix this stuff. So if there's anybody who wants to help me understand how to fix this stuff, well, I'd be nice to have a chat. Okay. Now, this is a very fair counter-argument here, is that, wait, can't you do the same expectation trick in classical mechanics, right? We did all these things with distributions, and then we converted to wave function, but, you were still be able to do it in distribution. Can't you do this in classical mechanics? And this does not mean, we have the same problem in classical mechanics, therefore we shouldn't care. No, we should, if it's a problem, maybe if it's a real problem that we can also do it in classical mechanics, then we have to fix classical mechanics as well, right? Because one of the arguments of the reviewer was saying, well, this problem is there in classical mechanics too, so it shouldn't matter. Like, as if, yeah, they stole your car, but, they stole also the other guy's car, so, it's fine. No, it's not fine. If it's a problem that both of things have it, we have to solve the problem. So technically, yes, we can do this trick with distribution in classical mechanics as well. But in classical mechanics, you can always have distribution with compact support, right? So you can always take a distribution and chop it up and just consider a part that it's in a bounded region. And then, of course, since the region is bounded, the state is bounded, then all the expectation of all the function of position of momentum are going to be finite, right? And this is kind of like in classical mechanics, that's how you think about distribution that go to infinity. Yeah, they don't really go to infinity. There is a cutoff. But I don't care where the cutoff is, but I could always put it. I can always put the cutoff. And so it's fine. So in classical mechanics, you can argue that all the physical states, right, are actually finite, but then you can make this infinite distribution, but the infinite distribution doesn't really exist, blah, blah. You can get away with it. The problem is that in quantum mechanics, you can't. Because in quantum mechanics you cannot make a cutoff in space without extending the distribution on momentum towards infinity. That's the issue. There is this Pauli-Wiener theorem, I don't know if it's pronounced correctly. The Fourier transform of a function of compact support is what is called an entire function. Like it happens to be an entire function. An entire function is a class of functions, which you can go and look it up. But the point is that an entire function does not have a compact support. An entire function goes off to infinity. So if you say, well, I take the wave function and I chop it off in space so that all the expectations in space are finite, you might have made the expectation in positional finite. And I don't know what is going to happen to the expectation of the polynomial of positional momentum. The issue is that if you were to require that the expectation of all the functions of position and momentum are finite, right, that is exactly asking that you have compact support. That's the only way that you're going to have a distribution in position and momentum where all the functions, the expectation of all functions of position and momentum are going to be finite. You can't do it in quantum mechanics. And again, I think, every problem is an opportunity. I think this is maybe telling us something about the physics. This is something important in the same vein of the uncertainty principle. There is something here. And I think it's worth exploring to not just fix the math, I really think to understand the physics better. So, okay, are there alternatives? Or we're doomed? Like, right, if you say, okay, well, we have this problem, but we don't know how to solve it. Yeah, I do not know how to solve it. But there are examples of classes of functions, right? The things that are in the Hilbert space, that are vector spaces, that have an inner product, but they have nicer property. So one option that is going to work if we are limiting ourselves to Rn is to require the expectation of all polynomials of position and momentum to be finite. So not all functions, because as we saw before, we can't do that, but we could require all the expectation, all the polynomial of position and momentum to be finite. This gives you the Schwartz space. What is the Schwartz space? The Schwartz space is the space of infinitely differentiable functions that go to zero at infinity faster than any polynomial. Faster than any polynomial means that if I multiply it by a polynomial and integrate, I still get a finite value, so I get a finite expectation. They have to be infinitely differentiable because remember that the momentum operator is the derivative. And so if I want to be able to have the expectation of all the powers of momentum be well defined, then I have to be infinitely differentiable. For any n, I need to be able to take the derivative. So this is a nice space, and it has some nice properties. First of all the elements are fully identified by the expectation. In fact, the topology is also defined by those expectations. So it kind of tells you that you can do what's called quantum tomography on these functions, on these states, right? Quantum tomography is the ability to reconstruct the initial state by looking at all the expectation of essentially all the polynomials of the quantities, the conjugate quantities, and you measure all of those, and you're going to be able to reconstruct the original state. So basically, you're saying I'm able to do quantum tomography, and that's kind of physically motivated. It makes sense. It is an inner product space, right? So it's a vector space and it has an inner product, and it is the same norm as L2, right? The Schwartz space is a subset of the Hilbert space of L square, and also it's a dense subset, meaning that every element in the Hilbert space can be seen as a Cauchy sequence of Schwartz functions. So once you know what happens to the Schwartz functions, you know essentially what happens to all the points of the Hilbert space anyway. In fact, the closure under Cauchy sequences recovers the Hilbert space, right? And so, well, essentially, you can think about it that you have a sequence of, of Schwartz functions, and if the expectation of all the polynomial position momentum of the sequence converges to a finite value, then you converge in the Schwartz space. If one of them blows to infinity, then you are not in the Schwartz space, you go to the Hilbert space, right? So again, it makes sense. It's exactly when you go out of the space, it's exactly when we have this problem with infinity. Another nice thing is that the Schwartz space on Rn is different of the Schwartz space of Rm if n and m are different. So the topology knows about this differentiability, knows about how many degrees of freedoms are there, and therefore it's more physically meaningful. It is closed under Fourier transform, meaning that the Fourier transform of a Schwartz function is another Schwartz function, which means that we can have a representation of position and momentum. And it plays a fundamental role in the theory of distribution. Typically, objects like the delta functions that are not even in the Hilbert space, they are in the dual of the Schwartz space. You can basically think of the delta function as a function defined on a Schwartz function, right? It's a map from a Schwartz function to a number, and that's going to be your delta function. So all these things are defined in top of Schwartz spaces. So all the theory of temporal distribution, all this good stuff that we also use in control signal processing and all this, already assumes that the Schwartz functions are important. That's how I know Schwartz functions. I don't know them from the physics. I know because as an engineer, I studied signal processes. That's where I learned these things. And most physicists have never even heard what the Schwartz functions are. And things like the Hermite polynomial, the Gaussians, and the Hermite polynomial are the solution to the harmonic oscillator. They are Schwartz functions. So a lot of the functions that you think are well behaved and we use in physics and so on happen to be Schwartz functions. So go Schwartz function. The problem is this cannot just be the solution, right? So if you imagine that we're doing a quantum field theory, right? Yes, we are going to have space, but then we also have a different number of particles, and now we're making a superposition between elements of different number of particles, right? And while we can think that every element that have the same number of particles is an element of a Schwartz space, when we are taking the superposition and we're taking linear combination of these two Schwartz spaces, we are going to be outside. And I don't know what is the correct closure. Right? I don't know. It might be that it's the correct closure is given by what are the possible transformation that we are allowing, right? And that's something that I don't know, right? If we're restricting ourselves to polynomials, it's clear that we're going to also have to rule out some unitary evolutions, the one or coordinate transformation, a coordinate transformation that transform as we had before, a Gaussian into something that is not a Gauss anymore. That has to be removed because it's not going to map a state to a state. So we're going to look at a space of unitary transformation that is more restrictive, which may be exactly what we want, but also means that relativistically we are doing something. We are saying there is a special class of coordinate transformation that are valid, and these other things don't quite make sense. But then maybe it's one of the reasons why it's difficult to make statistical mechanics and stuff like this in relativity and general relativity. Maybe it's because we are allowing even there too many coordinate transformations. I don't know. The point is we should be looking at these things. Like the mathematicians by themselves without any guidance of what is physical, what do we need in physics, they're never going to give us the right space because they're not physicists, they're mathematicians. And they're going to look at definition of things that are convenient for them to prove theorem, to find cool mathematical stuff. And it may or may not be useful for physics. It is up to us that we want to do physics to understand all these details. I mean, not all of you. I'm not saying that all physicists have to know everything about this, but we should have at least a small part of our community that looks at these things in detail and try to understand, okay, if we make this mathematical choice, we're going to bump into these problems. Are these problems fine to have or not fine to have? What are the options? And consult with mathematicians like I do to go and try to find the correct solution. And you'll find that there are a lot of mathematicians that are dying to do this work. And so if you want and you think that this work is useful, again, you can subscribe to this channel and we'll see all the updates of what things we were doing. We also have another channel in which I actually tend to do the research in the open so that we can have discussion. If you know of people that are trying to solve these things and they want to have a discussion, put them in contact. I really think that we have to bring together like sharp minds to analyze this problem. Not even claiming that I'm the one that has to solve this problem, but somebody's got to do it. Otherwise, we're never going to have a foundation of quantum mechanics that is physically meaningful, that it's mathematically precise, and that it's conceptually consistent. We're going to drag with this mess that we have at all different fronts and never reach any stable place. So thank you again for your attention and see you next time.